It's a good time now to discuss the database design for our domain model. We currently have only two classes in it, Snack Machine and Money. We need to decide which of their properties we want to persist in the database. That is another subject for discussion with a domain expert, because such decisions would affect the overall model behavior. For example, if we decide to store both money properties, that would mean we want to save the model's state not only between the transactions, but also in the middle of it. Let's assume that we, together with the domain expert, decided that it's okay for the machine model to be persisted only when a transaction is completed. In other words, when the purchase is done. So we're not really interested in saving the money in transaction property in this case. We assume that if the application crashes before a user completes a purchase, it's fine for the model to lose the track of the money that wasn't sorted before this point. Alright, that leaves us with two classes, the Snack Machine entity with a single field and the money value object with 6 fields. How would the database look in this case? One of the options that might come to mind is to create separate tables for each of them, like this. You can see the Snack Machine table in this diagram contains a reference to the money table. While this might seem a good idea, such design has two major drawbacks. First of all, the money table contains an identifier. It means that we will have to introduce a separate ID field in our domain model in order to be able to work with such table correctly. This in turn means that we need to give the money value object some identity, and that violates the definition of value object. The other drawback is that with this solution we can potentially detach value objects from entities. The money value object can now live by its own because we are able to delete a Snack Machine row from the database without deleting a corresponding money row. That would be a violation of another rule which states that the lifetime of value objects should fully depend on the lifetime of their parent entities. It turns out that the best solution in this case is to inline the fields from the money table to the Snack Machine table, like this. This would solve all the problems I stated earlier. We don't give an identity to the money value object, and its lifetime now fully depends on the lifetime of the Snack Machine entity. And it makes sense if you mentally replace all the fields that regard to money with a single integer, as I suggested in the previous module. Do you create a separate table for an integer? Of course not, you just inline that integer to the table you want it to be in. The same applies to the value objects. Don't introduce separate tables for them, just inline them into the parent entities table. So now, as we've come up with a database structure for our domain model, let's see how to link them together. In this course, we'll be using NHibernate as an object relational mapper, so let's install corresponding NuGet packages. The first one would be the NHibernate library itself, and the second one is Fluent NHibernate, which enables fluent mapping for our domain classes. We will talk about different mapping strategies in a few minutes. To make NHibernate work, we need to introduce some auxiliary code, namely Session Factory. I'm copying its implementation here. Let's walk through it together. One of the key elements in most ORMs is the notion of session. You might have heard of it as context if you use such mappers as Entity Framework or Link2SQL. It keeps track of all objects loaded from the database into memory and automatically updates the corresponding rows in the database according to the changes made to those objects. Session implements the unit of work design pattern, meaning that it pushes all accumulated changes at once, usually at the end of its lifetime. Also, it is lightweight and designed to be created and disposed of frequently. A common guideline for working with sessions is to create a separate session for each interaction which takes place between the user and the application. Session Factory, on the other hand, is a heavyweight class. There should be only a single instance of it per each database. Here we introduce the initialization method that takes a connection string, creates an instance of the Session Factory, and saves it in the static field for the later use. The build Session Factory method uses Fluent NHibernate library to fluently configure the ORM. You can see here we specify that our application uses a SQL Server database, And Hibernate supports most of the popular relational databases, so you can use it with any other database, for example Oracle or MySQL. With this line, we tell in Hibernate to get the mappings from the current assembly, and we also specify some useful conventions. For example, here we are saying that all referenced entities should have a corresponding column name that ends with ID. All fields in the database should be treated as non-nullable by default, and all tables should have the same names as the corresponding entities classes. With such conventions, we reduce the amount of repeatable work needed to set up the mappings between our domain classes and the database tables. A more interesting convention here is the one that regards to identifier generation. But before explaining what this convention means, let's discuss different ID generation strategies. There are three popular methods to implement ID generation for domain entities with SQL Server. One of them is to rely on the SQL Server's identity feature. We can define an ID column in such a way that every time we insert a new row, SQL Server will attach a new identifier to it. So when we create a new entity in the memory and then save it, the ORM pushes a new insert to the database. The database generates a new identifier which the ORM then retrieves and assigns to the entity in the memory. While this solution allows us to leverage the built-in SQL Server functionality and generate good-looking integer values, it has a major drawback. In order to actually assign an identifier to an entity, Hibernate has to perform a round trip to the database, and that doesn't play well with the concept of unit of work. It means that in some cases we are no longer able to execute all changes made during a session at once. Another way to generate an identifier is to use GUIDs. It doesn't contain the drawback I described because GUIDs can be easily generated on the client side, so there is no need to make a round trip to the server. The only shortcoming with this approach is GUIDs themselves. They may be cumbersome to work with, and you might prefer to have integer identifiers instead. If this is the case, you can use the third option, high-low algorithm. The idea behind this algorithm is that you can devote to the client not just a single ID, but a whole batch of identifiers at once, which then can be distributed among new entities. This is usually done by having two numbers, high and low. High is the number of the batch, whereas low is the number of identifier in that batch. High numbers are stored in the database. So for example, let's say that the batch size is 10 and the current high number is 5. When a client application is about to set a new ID to an entity, it increments the high number stored in the database and thus gets the batch number 5 with the identifiers ranging from 50 to 59. The client then can safely use these identifiers to assign to new entities, knowing that they are reserved for it exclusively. This approach also means that we need to have a separate table to keep track of the batches that have been issued so far, like this. You can see there is a row for the Snack Machine entity. Basically, all entities in our model will have separate rows here. You can check out this Stack Overflow answer if you want to learn more about the high-low algorithm. Generally speaking, it is mostly a matter of taste whether you choose GUIDs or high-low. For this course I use the high-low algorithm, but it's perfectly fine if you prefer GUIDs instead. So, returning to the convention for our session factory, you can see now what all of these parameters mean. This is the name of the table where all batch numbers are stored. This is the column name for the batch number itself. This is the size of the batches, and this is the filter statement. It is used to determine which of the rows Hibernate should look into to get the next ID for a given entity. There are three approaches when it comes to mapping domain entities to tables in the database: XML files, attributes, and fluent mapping. XML files are quite verbose and are prone to break when refactoring because they operate literal strings to define the names of the properties being mapped. Attributes is a better option. They don't have the shortcomings of XML files, but they do have another one. Remember, we talked about the importance of isolation. We discussed that the innermost layer of the onion architecture, entities, value objects, aggregates, and domain events, should have a single responsibility, which is representing the domain knowledge of your system. Adding mapping attributes directly to entities means they start holding the knowledge about how they are being stored in the database. Therefore, this mapping strategy violates the single responsibility principle. Because of that, we are better off choosing the fluent mapping approach. With this approach, we can create separate map files for each entity. So let's create one for the snack machine. I call it snack machine map. The map file itself would look like this. You can see the ID field is mapped using the ID method, which allows us to specify the identifier property for the entity. Also note that we map only the money inside property, we don't store the money in transaction field. The component method is the method that allows us to inline the value objects fields into the parent entities table. You can see we list all 6 properties here. That means each of them has a separate column in the snack machine table.